Okay, alright, let's continue. So last time we talked about what is the chi-square distribution and how could we compute it. So last time we are left with this formula. That one. The chi-square is the sum of the difference between the expected count and the observed count square. Of course, because we want positive value, and then divided by the size of the expected count, and then explain how each why do you have the minus sign, why do you have the square, why do we have to divide it by the expected count, the EI. So now let's take a look at quick examples. So let's say we have a quick survey for students. Yeah, that's for. So simply we have like 4 different age ranges: 15 to 18, 19 to 21, 22 to 25, and 26 to 29. Right. So this is what we got, and suppose we have some other thing in mind. So we thought that all these 4 age ranges should have the same amount of students. Okay, so we expect this one to be uniformly distributed. But as you can see, the number is pretty much not what we expect. So, but we cannot just say, okay, the number is that these 4 numbers are different, so our hypothesis was false. Right, we cannot just say that, so we have to translate this into some p-value, some single number, and then we can use that single number to make a decision. So we just for the first part, we just focus on how to compute the chi-square values. Right. So now we have a blank one. So what we expect here? Oh, I forgot to put this in. Okay. So we have to say what we expect. Okay. What we had in mind. This is what we have to stage before we take samples. Right. So we have to first say what we have expected. Right. And once we fill in these entries, these 4 values, then we can take samples and perform hypothesis testing. So what we have here, we have also the total number is 28. So we do a quick survey for 28 students on campus or wherever you want to, right? And I'm not sure about the others, but let's say there are 4 ranges, right? Since the total is 28. Okay. And we expect that each of these 4 ranges should contain the same amount, the same number of students. So we would have thought that, okay, if we do a survey, then we should see 7 students in each category, in each age range. Right. So we have this number first, right? And then we do a survey, and what we got back from the observed value or from the actual sample is that there are 2, 13, 10, and 3. So now this is what we observe. Okay, just observe. Or survey or sample or the numbers that you get from actually asking people. So these 2 numbers seem different, but are they different enough so that we can reject our hypothesis? So now we have to compute the chi-square. And if you go back all the way to the 2 or 3 slides before this one, we have to take the difference between these 2 values. Oh, and you can see that in this case we don't care what age ranges are there. So this one, 15, 19, 22, 26. 15, 19, 22, 26. Right. We don't care about the numbers on top, because now we only care about the differences of these 4. Right. And you can also notice that the lengths of each range are different. This one has the difference is 3. So the range is half size for 15, 16, 17, and 18. Right. This one has size 3, 19, 20, 21. And this one has 4. This one has 4. So now we we can perform this even if like these numbers are different, even if they are like widely different categories. So what do we do here? The formula is we take the difference between the the expected value, right? Subtract that from, find the difference between that and the observed values. Okay. Because we wanted to see if these gaps are too large, and then we square it so we get a positive number, and then we divide it by the expected value. Sorry, it's the expected count. And what do we have expected? And we take the summation, and this is just one term. We have to take this for all 4 terms, so that from 1 to 4. That means we have to compute this for 4 different ranges. The first one is is here. Simply you take 7 and subtract it by 2, and then divide it by 7, and the whole thing square. It's as simple as that. The difference square, and then you normalize it divided by the number, the size that you have expected. So you do the same for the rest. Let me move it here instead. Alright, so chi-square is, what's the first one? Is we have 7 right, minus 2. 7 minus 2 squared divided by 7. In the second one, it is still 7 because our hypothesis, we believe that these numbers should have, these age ranges should contain the same amount, the same number of students. But for the second one, we have 13. So just put 13 there and squared, and then repeat for the other two. Right? We expect to see 7, right? But we actually see 10. So that's 7 minus 10, the whole thing squared divided by 7. And finally, again we have 7. And our sample use 3 square. Now this 4 values, the sum of these 4 values is what we want. Is the chi-square. Okay, so that's 7 minus 2 is 5. 5 squared is 25. 25 divided by 7, and that's 6 squared is 36. That's 3 minus 3 squared is 9. Oh, it's 9. And finally 4 squared is 16. As you can see, we have 4 different numbers. So that's 25 plus 36, 61, 70, 86. So we have 86 divided by 7, which is about, I think, 12 plus 2, 8 or something. So now we get a single number, which is 12 plus 2, 8. And that's done. That's the first part. We have to compute something. We want to compute the test statistics, and that test statistics, that chi-square is 12.28. And then we have to interpret whether 12.28 is high or low or whatever. Let me make sure I got the right number by looking at my slides. Yeah, 12.28 is. And that's it. And then we similarly after this we have to compute for the p-value. The p is just the one we want to. It's gonna be something like what we have seen. So for the normal distribution, we see that, right? This is the statistics we got. For the chi-square, we still have the same principle. But now this is replaced by chi-square, and that is replaced. This is the value, the test statistics that we have computed, which is 12.28. And then we can look up at the chi-square table for with degree of freedom 3. whatever table it is, to see what this gives us, and that value, the final value from the table, is the p value that we want. But we are not going to touch there. Once you can get 12.28, right? Everything else is just a call. It's no longer math. Right? You get that number, you look up the table, you compare that with the alpha, and you say whether you reject or not. Right? Everything else is just a short. We can leave it to PC, computer, calculator, or whatever. But the first step that we sometimes have to compute by hand is here. That you have to understand what this number 12.28 means. And to recap, the higher the number is, right, the more differences there are from what we believe, the green one, to the sample tells us, the pink one. If ideally, if that number is 0, right, if we believe all these 4 categories should have 7 students, and we do a quick survey, and we actually got 7, then this chi-square will become 0. Right? And then that 0 is ideal. Right? That means that the lower the number is, the more likely that the survey agrees with what we have believed. But as you can see, 12 looks high, and you can just look at it and intuitively conclude that the number from the expected number, what we have believed, and the sample are too much different, which means eventually we would have reject the original hypothesis. And this is just the same one. Yeah. So the ideas are the same. You have some counts, right? And the nice thing is you don't assume anything else. You don't assume that this is normally distributed. You don't assume that. You don't assume that you don't require at least 30 samples. And this one we have to at least 28, and we can perform that. Just a quick number that we can work on. Okay. So now that's just a brief example on how we can compute a chi-square. Okay. We have observed counts, we have expected count, and we combine them and get a single number. Right. And what can we do with that? That's the main question. Like, can you may ask, can't we just stick with the normal distribution? Right. But we have to bother with the chi-square. It is like more complicated because it can solve these types of problems. As you can see on the top, like we have 1, 2, 3, and 2 extras. Okay. These are 5 main problems that you encounter and that you can use chi-square test. Right. The first one is called the goodness of fit test. Like the name doesn't kind of make sense, but like if you translate it into like just the question, does it fit? Well, yeah, but maybe that question is easier to interpret. So we have like the core concept, like what would you say, the basic classic question. So you just look at these comics, and you may have noticed that I enjoy taking comics from XKCD. Right. So one of the questions in statistics is that we have a not so nice samples. From what you can see from there is we have a graph. We have a relationship for 2 different categories. And we want to kind of somehow draw a trend. We want to predict the future or see if they have any relationship between them. And if we just look at the black dots, we can draw whatever we want to. For in the first one we draw a nice line, and this is called a linear regression, which you would have studied in the basic statistics. This is the intro, so you don't see it, but in the next course, in the more advanced course, or if you go into data science or AI or whatever, one of the very first courses is linear regression. So that's that. Okay. So this is what we are comparing. We are comparing two things again. We have the black dots, which is the sample, and we have the red lines, which is the expected trend. And let's use the word trend. Yeah, these two things. And when you wanted to say if these two things look close enough to each other, if maybe we expect it to be a linear, you draw a line. We might expect it to be a quadratic, logarithmic, or whatever line you want to. If you look at the full comics, they have like 12 or 9 more. Yeah. So again, the question is the red line aligning well enough with the black dots? That's pretty much like the question, which you can understand visually, right? You don't have to know math to be able to kind of answer if the black dots seem to align with the red lines. Right. Sorry about what of text again. So the question is, that's the definition, but we instead of dealing with the parameters, the mu, chi, theta, pi, whatever, we deal with the distribution. We are asking if the sample agrees with the distribution that we believe in the first place. So how well our data support the assumption about the distribution. So this data is represented by the black dots above. The distribution is represented by the red line or lines, because we have 3 or more. And when we state our hypothesis, it is on this form. So we believe, right, for H now, what we believe that this population or this population has a normal distribution. Right. So this means we believe that the line, the red line, should be something like that 21. Right. And H1 or the alternate hypothesis is the opposite of that, which is it does not has a normal distribution. It can be anything else, right? We don't know, because we have no idea, but we believe, if you believe it is normal, then the opposite of that is not normal. And that is not, this is just the hypothesis here. And as you can read here, we can replace the normal by any type of distribution. We may believe that the population has a binomial distribution. We may believe that the population has a geometric distribution. We may believe that the population has a Poisson distribution, or uniform distribution, or whatever. We put that word there. And then once we establish our hypothesis, then again we can go out and take samples and see if that agrees with H now. And since there are all the types of distributions, and each of them have different test statistics, different way to compute, then we cannot just list them all. But we can give one example that we can actually compute. Yeah. So this is example of the multinomial distribution, which if you go back to lecture 10 or 11, it was there. Okay, just to recap, that multinomial distribution is that we believe then we believe that let's just say like a box, like this box has 5 different numbers, and we believe that each number have different amount of balls. Or in other words, each number has different probability of being drawn from the box. Okay, so we believe that we have like let's say just 3 boxes, and this box, oh sorry, not 3 boxes. I mean we believe that there's one big box, and we believe that the probability of getting maybe a ball with number 1 is maybe 0.2. The probability of getting a ball number 2 is 0.5, and we believe that there is a 0.3 chance to get a ball with number 3. This box has like lots of balls. It is what we call a multinomial distribution, which is similar to binomial. Right? If you look at the word origin, binomial, multinomial, right? They are the same nominal thing. But instead of bi, which is 2, now we have multi, which is 2 or 3 or more. Okay, so this will have like different p's. So we can state that in terms of this one. Oh yeah, let's take a look at the next page. We can believe we may state our null hypothesis this way. So we believe that the probabilities of occurrence of events, or like Bottas balls, A1 through AK, are given by the specified probabilities P1 through PK. Just the same as the balls. Right? We believe the ball A1 has P1 chance to be picked, A2 has P2 chance to be picked, and so on. Which actually we can. I think I have that here. Oh, sorry, yeah. Is this actually that? Is this? Let me go back to the. Yeah. Oh, to rephrase, it means we are saying that the population has. Wait, why is that? Okay. Multinomial distribution. So this is what we are saying. Right. But we are saying more. We are saying that it has a multinomial distribution with these specified chances. This is fine. You can write it this way, but that's gonna be kind of vague, I think. Oh, sorry. Yeah. You have to say that, and then you have to specify each pi, p1, p2, all the way up to p of k. And if we believe that each category, each event A1 to AK have this chance, then if we repeat the experiment, or let's say if you pick a ball from the box n times, we perform, let's say, n trials. Right. If the first box has a chance FP1 probability to be picked, then the number of balls that we expect to see is P1 times n. And that's just the definition of probability. And then for the P2 we have P2 times n. For the P3 we have P3 times n, and so on up to PK times n. Oh, by the way, yeah, this is what we state. We all state up here. This is what we have believed. Right? And then from that we can transform that sentence into the expected count for each event, and A1, N2, A3, AK. Sorry, A1, A2, A3 up to AK. Right. So for example, let's look at this table, right? Just at glance, don't read anything. Just look at glance. We are given again. We are given this for numbers for counts, right? Then we have to see if these numbers make sense or these numbers agree with what we have believed. So let's go back and count. Let's go back and read now, right? Raymondville, I think it's a watch brand. Right? So this company is trying to get come up with a new watch, this kind of watch, right? And see if people would prefer specific color. Right? So they are releasing 4 different colors, right? And usually, if you don't have any idea, you would release each color with the same quality. And so if you have to produce 1 million watches, and you would produce 250,000 for each color. That's even easy to do. But if they believe that some color is more preferred, like if you think that people prefer black or prefer brown, then they can adjust these numbers. Like if they produce the same number, then one of the watches, one of the colors would like deplete fast, and then they will have like an excess of one color that no one wants. So they want to do the survey and to make sure they produce the right amount of watches in each color. So they have a survey of 80 watch buyers, which is small. Like usually, if you do a market research, the number should be like at least 100, 200. But maybe this watch is too expensive that nobody buys them anyway. So they can only find 80 people to do the survey, right? And this is the list. So for 12 people prefer tan, 40 people prefer brown, 8 people prefer maroon, and 20 people prefer black. Yeah. This is the survey, the observed count, right? And then we believe, right? Again, we have to put this first before we do any survey. If we believe that half of the watch buyers prefer brown, okay. So now we believe these 4 are not equal. We believe more people should buy brown watches, okay. And then we believe that the rest, the other 3, are equally likely. Okay. Then how would we make a decision whether what we believe is likely or not? Right. So again, we have to conduct hypothesis testing. Right. So at first, again, we have to state precisely what our hypothesis is. In this case, again, since this is a multinomial distribution, we can say the population has a multinomial distribution. Right. And this is the goodness of this test is about. And since this is a multinomial, we have to specify each event, right? Where, so we have four colors, right? P1, P2, P3, and P4. For the multinomial, we have to be precise on each of the probabilities. So we believe that half of them would prefer brown. So we believe that it is a half. Maybe we believe we have a 50% chance of picking a person, a watch buyer that prefers brown. And we have 10 brown, maroon, black. Let's do it this way. We have 10. We have brown. We have maroon, and we have black. Okay, here we go. That's less ambiguous. Right. If it is 1/2, then okay, we have to compute a little bit. Right? We have if 1/2 is brown, right? that means the rest is also a half. But since the rest has 3 different colors, 3 different categories, so you have to split this 1/2 into 3 probabilities, and since each of these one has the same chance, so they each have 1/3 chance, but is it 1/3 of 1/2, right? Because we only have 1/2. Let's think of it as like one. Oh yeah, let's think of it as like we have, let's look at this pie chart. So half of this is brown, right? The rest is the rest, but since we believe that the rest is divided into 3 equal pieces, we have tan, maroon, and black. So that means it is tan. We believe this is maroon, and this is black. And as you can see from the pie chart, this is if this is 1/2, this is 1/6. It is 1/3 of 1/2. We cut it in half first, and then we cut that half into a third. So that means each of these pie pieces is 1/6 of the whole pie, or of the whole population. Okay. So that means we believe that the rest is 1/6, 1/6, 1/6. Yeah. So now we take a look at and see if this is all we have to state in at first. Okay. So we say it's multinomial distribution, but that's not enough. We have to say further. We have to say multinomial distribution with this given probability, and we believe that's that's correct. So for H1, it is of course you can just say it's the opposite of H2, right? But in this case, we have to be careful. Right? The opposite of that is not just. Oh, sorry, that's wrong color. The opposite of that is not just saying that the population doesn't have a multinomial distribution. Let me hear this in the way. Right. This is not the opposite of the first sentence. Right. Because as you can see, the first sentence also has like this requirement. So we have to also add the requirement. So I think we can copy that whole thing. Yeah, I'm gonna be lazy. Copy paste. Oh no! I mean that works, but that brings us all the way to the end of it. Ouch! That brings us all the way to the end of the lecture. Give me a moment to. Oh, maybe that. Okay, here we go. So the opposite is that this doesn't have a multinomial distribution of this with these 4 probabilities. Okay. What does it mean here? It can mean 2 things, right? H1 means we have the first case, right? It means that the population doesn't have doesn't have a multinomial distribution, right? This is just one half of that sentence. Yeah. Maybe it has a binomial distribution. Oh, sorry. binary multinomial. Maybe it has a Poisson, maybe it is uniform, it is no, it is normally distributed, maybe it's geometric or whatever different distribution, or it might mean that it does have a multinomial distribution, but with different PIs, right? So that it means it either doesn't have a multinomial distribution at all, or it has a multinomial distribution but with different PI. Again, we are testing for the big picture. Like, we are not testing for each P separately, like, because that can be done with the normal distribution. But we are looking at the whole picture. Okay. And if that whole picture doesn't agree with what we have to leave, like even if three of them agree but the first one doesn't agree, then we still reject the idea. And we reject that it agrees with the big picture that we have. Think of it as the graph that we have up there. Yeah, like that. Okay. So in this case, maybe some of the points are outside. Right? Some of them do not agree, but if most of them agree enough, then we say they agree. Right? And on the other hand, sometimes most of them agree, but we have some outlier, like one of the black dot is like all the way up there. Can you see that? Yeah, up there. From this graph, comparing to this graph. And then when we might reject our red line, we reject our belief, the trend that we have in mind. Right. So now that's the hypothesis here. And how can we test that? Then again, we create a table for this too. So we have the expected probabilities. Let's say probs, right? Or EI. We expect the brown one to be 1/2. Is it the right entry? Yeah, to be 1/2, and then we expect the rest to be 1/6. And this is what we should have to settle before we perform the experiment. That's a brown. Okay, the rest. And what we have observed from the survey O of I is different, but now you can see that okay, we have like 1/2, 1/6 here, but now we have a whole number 12, 40, x 20. That means we have to convert that number. You have to first convert that number into the ratio, or the probability. And to do that, we just simply divide the whole thing by 80. So we can get a proportion, the ratio of the proportion. So that's 12, 40, 8, 20. Let's take another 12, 40, 8, 20. So this one would be 12 divided by 80. And we can cancel this thing to get 3 over 20. This one is 40 over 80, or 1/2, which happens to be exact. Okay. The third one is 8 over 80, which is 1/10, and the last one is 20 over 80, which is 1/4. Now we have two numbers that we can compare, right? 1/2, 1/6, 1/6, 3/20, 1/2, 1/2, 1/6, 1/10, 1/6, 1/4. So now we can then compute the chi-square, like as before. What is a chi-square? We take the difference, like for each category. The first one will be 1/6. Right? Subtract 3. Oh, wrong color. Subtract 3/20. like square divided by the expected count, which is 1/6. So this is the number for the first one, and then we simply repeat this for repeat that for each of the 4 categories. And this one we have 1/2. This one we have 1/6. This one we have 1/6 again. And this is what we have expected. What we need square for each bracket. And what we have observed there is let's say 1/2, 1/10, 1/4. 1/2, 1/10, 1/4. Oops. And that's a formula to compute the chi-square. And we just simply use calculator or whatever. Like this is 1/2, 1/2. Like these two cancel out, so that's 0. This is 1/6 subtract 320. So let's do just the first one. Like what is 1/6? 1 over 1/6. So we can split the 6 up to get the 6. Right. 1/6 subtract 320. So that's different denominator. So we find LCM, least common multiplier, which is 60. So that becomes 10 over 60. That becomes 9 over 60 square. And for the next one, that's 0. Next one is I think it's 5 over 30. And that's 3 over 30 square. I am not sure if my head is too big or I'm writing too large. My last one is 6 times 1/6, 1/4, we have 1/12, so that becomes 2/12, that becomes 3/12 square. Okay, let's zoom out a little bit. Here we go. Now this whole thing will give us one single value for the chi-square. Be careful that this is a chi-square. It is not a p-value yet. And I'm losing the 5. Anyway, it's gonna. I think it's like 0.07 or something. Right. So that is the chi-square that we got. Then again, we have to find the p-value. This is the probability that this chi-square is less than 0.07. And then that is the p-value that we will compare with the alpha. And so that's it for the goodness of it. This is similar to the very first definition of chi-square. We just have to rephrase some of the words so that we can use the chi-square test to get a meaningful decision. So that's the first one. So we are going to next one. We are going to look at the independence test.